Okay, for what we have in number 16, we have y prime is equal to the square root of x plus y plus 1. And now we don't have a Bernoulli equation, and we don't have a separable differential equation. And so this is a different kind of v substitution item. And what we can do in the setup, okay, first of all, we can say that v is equal to x plus y plus 1. And again, we don't have this to be a homogeneous equation either. So letting v be equal to x plus y plus 1, and if we take the derivative of the terms with respect to x, so you're going to have that dv over dx is equal to 1 plus, and the derivative with respect to x of y is going to be dy over dx, and for 1 the derivative cancels out. Okay, so we have from the setup here, we got dy over dx is equal to dv over dx minus 1 and for what we have from the original equation, okay, so we have dy over dx is equal to, and if you notice you had the square root of what we have substituted v for, or substituted with v for. Okay, and so we have for the square root of v, okay, so that's going to be v raised to the 1/2. And if I tie in together what we have in defining dy over dx, so we have dv over dx minus 1 represents dy over dx, as does v to the 1/2. And if I look at isolating the derivative, so if I add 1 to both ends, so we have dv over dx is equal to v to the 1/2 plus 1. And looking at separating the variables, so I have dv all over v to the 1/2 plus 1 is equal to dx. And if I look at integrating on both sides, I tell you what, I'm going to go ahead and write v to the 1/2 as the square root of v. Okay, so you have integrating over both sides. Now for what I have to the left, okay, this is a bit of a challenge. And just working over to the side here, so you have dv over the square root of v plus 1 we had the square root of v separated from 1, and what I can do is that I can rewrite this ratio so I can just say that I have like 1 over the square root of v plus 1 and do something akin to taking conjugates. Or something that has a feel of about like difference of squares, like a plus b, a minus b. So this will come down to the integral, where I have the square root of v minus 1, and we have all over square root of v times itself, that will be v, and we have minus square root of v plus square root of v, that will cancel out, and we have minus 1, and we have dv. And if I look at performing a special kind of u substitution, so I will let u be equal to the square root of v, and if I square both sides, we have that u squared is equal to v, and taking the differential of both sides after squaring, we have 2u du is equal to dv. And taking what I have in the rewritten integral statement, so I got the integral of what is going to be u minus 1 and we have all over u squared minus 1 and for dv I have 2u du. And looking at what we have in the follow-through, if you notice, u squared minus 1 factors out to u plus 1, u minus 1. So we can have the u minus 1 to cancel. And if I multiply 1 by 2u du, so I have 2u du. And again, u minus 1's cancel, so I have 2u du all over u plus 1 now we have 2u over u plus 1, and the way that you could look at this, okay, is that for the layout here. So you have 2u, you're just a couple of units short of being double u plus 1. So if I were to provide a bit of separation, so you have like 2u plus 2, and I have minus 2 over u plus 1, quantity du. Well, guess what? In terms of simplifying, okay, so 2u plus 2 minus 2, that goes back to 2u, and you have all over u plus 1. Now for 2u plus 2 over u plus 1, so we have 2, we have minus 2 over u plus 1 du. So we come out to 2u minus 2 times the natural logarithm of the absolute value of u plus 1 followed by the constant, and back substituting, so we have 2 times the square root of v minus 2 times the natural logarithm of the square root of v followed by the addition of 1 followed by the constant. So we have, going back to our statement, okay, so left hand side, so we have 2 times the square root of v minus 2 times the natural logarithm of the absolute value of the square root of v followed by the addition of 1, and for the integral of dx, so this will become x plus c, and putting back in, and once again we had v to represent x plus y plus 1, so in this statement we'll have 2 times the square root of x plus y plus 1 minus 2 times the natural logarithm of the absolute value of the square root of x plus y plus 1 followed by the addition of 1 is equal to x plus c, and that is going to be the final result. For number 17, okay, we have y prime or dy over dx is equal to the square of the quantity of 4x plus y, and we don't have a homogeneous equation, and we don't have a nonlinear Bernoulli equation. And if we look at utilizing v substitution, so we can say that we have v is equal to 4x plus y, and just taking the derivative with respect to x. So I'm going to have dv over dx is equal to 4 plus dy over dx. And rewriting this statement in terms of dy over dx, that is equal to dv over dx minus 4. And having v to represent 4x plus y, we can say that for the derivative in terms of the variable v. So we have dy over dx is equal to v squared. And with both statements representing dy over dx, we can set up an equality statement where we have dv over dx minus 4 is equal to v squared, and getting the derivative by itself. So for dv over dx, we have is equal to 4 plus v squared, and separating the variables. So we have dv over 4 plus v squared is equal to dx, and we have integrating over both sides. So just as a reminder, okay, so if I have like the integral of du over a squared plus u squared, that's going to be 1 over a times the arctangent of u over a followed by the constant. And if you notice, we have for dv all over 4 plus v squared. Okay, this will be the same as dv over 2 squared plus the square of v, and 1 over a, that's going to be 1/2 of the arctangent of v over 2 followed by the constant. So just putting back, okay, so we've got 1/2 of the arctangent of v over 2 is equal to x plus c, and multiplying by 2. Okay, so we got, upon multiplying, we have the arctangent of v over 2 is equal to 2x, and for 2 times c, I'm just going to insert alpha. Let alpha represent 2c. And if I take the tangent of both sides, taking the tangent of both sides, tangent of arctangent of v over 2, that'll be v over 2. tangent of the quantity of 2x plus alpha and multiplying by 2. So we had that v is equal to 2 times the tangent of 2x plus alpha, and back substituting. So v represented 4x plus y. Here I can isolate y, or I can say that y is equal to negative 4x plus 2 times the tangent of the quantity of 2x plus alpha. Okay, for what we have in number 18, we have the quantity of x plus y times the derivative. Okay, y prime, or dy over dx, is equal to 1. And if I isolate the derivative, so I can just divide the equation by x plus y, and if I supply v substitution, letting v be equal to x plus y, and taking the derivative with respect to x, so I have dv over dx is equal to 1 plus dy over dx. We have in the rewrite, so I have dy over dx is equal to dv over dx minus 1. And with v representing x plus y, so we have dy over dx is equal to the reciprocal of v. And with these simultaneous equations, I got dv over dx minus 1 is equal to 1 over v, isolating dv over dx. So if I add 1 to 1 over v, okay, so what I'm going to have here is I'm going to end up with 1 over v plus 1, or 1 over v plus v over v. So that's going to be v plus 1 all over v, and then separating the variables. Okay, so dividing by v plus 1 over v, or multiplying by v over v plus 1. So I have v over v plus 1 dv is equal to dx. And for v over v plus 1, think of it kind of like, once again, like adding 1 and subtracting 1. So I'm just going to go ahead and write, whereupon I'm going to have 1 minus 1 over v plus 1 quantity dv is equal to dx, and integrating over both sides. So I'm going to have v minus the natural logarithm of the absolute value of v plus 1 is equal to x plus c. So we have x plus y minus the natural logarithm of the absolute value of x plus y plus 1 is equal to x plus c. And guess what? We have x's on opposite sides, so we can get these terms to cancel out. And you can leave the final answer in this form, but another way, if you were to get this y by itself, you're not separating the x and the y altogether. But if you were to get this y by itself, you would have that y is equal to the natural logarithm of the absolute value of x plus y plus 1 followed by the constant. Okay, for number 20, we got y squared dy over dx plus 2xy cubed is equal to 6x. And if I isolate the derivative, so taking 2xy cubed and also dividing by y squared, we have 6x minus 2xy cubed all over y squared. And then simplifying, we have dy over dx is equal to 6x over y squared minus 2xy. And if you notice, we have a linear term in y, and we got the derivative in the form of dy over dx. So we're going to have a Bernoulli equation and getting it into the standard form. So we have dy over dx plus 2xy is equal to 6x over y squared, and just to throw in, so you have like 6x times y to the negative 2. So your n value is equal to negative 2, and just some of the things that we have here, just to restate that we have a Bernoulli equation that is nonlinear. So you have like the p of x, like when we were working with first order linear differential equations, had the first order y term has a coefficient of 2x, and your q of x happens to be the numerator, which we have at 6x. And once again, setting things up and aligning where I'm going to use the substitution variable v. So we have in the layout, so we're going to have v is equal to y raised to the 1 minus n, and here we have n is at negative 2, and so you have that v is equal to y to the third And if I rewrite what I have in terms of y equals, well, I can take the cubic root of both sides and say that y is equal to v to the 1/3, and taking the derivative with respect to x. So I have dy over dx, and taking the derivative with respect to v and then with respect to x. So we have 1/3 of v to the negative 2/3 dv over dx. And for what we have in the standard form, so if I replace the terms in this equation and translate in line, or have it in terms of the substitution variable v, so dy over dx. Okay, so we have in the rewrite, we have 1/3 of v to the negative 2/3 dv over dx, and we have plus 2x times y. Y we have at v to the 1/3, so we're going to have plus 2x times v to the 1/3, and we have 6x times y to the negative 2, so we're going to have is equal to 6x, and if y is v to the 1/3, well, y to the negative 2 is going to be v to the negative 2/3. So this is what we have in substitution terms. And to get the first term in the form of just dv over dx, I can multiply the equation by 3v to the positive 2/3. So we have in the rewrite, so I got dv over dx plus, and what's going to be 6x times v to the first. So you have, for this equation, okay, so we got linear and v. So for the coefficient of the first order v term, we have 6x. For the integrating factor, so looking at e to the integral of rho x dx. So you have e to the integral of 6x dx. So you have e to the 3x squared, and multiplying this standard form by e to the 3x squared. Okay, so we have on the left hand side, okay, if you were to say distribute, well, we would have the product rule expansion of taking the derivative in x, multiplying the integrating factor, namely e to the 3x squared, times the dependent variable which we have with v. And again, we have is equal to 18x times e to the 3x squared, and taking the integral of both sides, so we have e to the 3x squared times v is equal to the integral, where we have 18x e to the 3x squared dx. And here we have e to the 3x squared times v, and the antiderivative of 18x e to the 3x squared, okay, that is going to be, in this case, right, so derivative of 3x squared goes to 6x, and into 18x will be 3 times. And dividing by e to the 3x squared, so this will become v is equal to 3 plus c times e to the negative 3x squared. And again, having used v to represent y to the third, so putting back, so you have y to the third is equal to 3 plus c times e to the negative 3x squared, and I can write this in terms of y, taking the cubic root of both sides, whereupon we have y is equal to the quantity of 3 plus c times e to the negative 3x squared, and all raised to the 1/3 power.